So let's see, first a couple of definitions. It will be real line, no high dimensional, not even two-dimensional things, and we will be in the dyadic world. We have the, well, family of the dyadic intervals there. What we will need is, I will refer to I and J being dyadic intervals, capital I, capital and capital J. Well, I need Haar functions. My Haar functions will be normalized in L2. We need to, you know, well, say A plus will be the left side, A minus will be the right side, to decide which one will be which from the beginning, right? That is not very important, it doesn't matter, right? And let's see, I will use the f sub I notation for the integral over the dyadic interval I of a function f. I will use m sub I of f for the average. And f dot g, the dot product is the angle parenthesis, okay? All right, we need the definition of the A2, the Mackenhaupt class, A2. We define the A2 constant of W as a supremum over all dyadic intervals. It's a dyadic A2. I missed the D, but I hope it's not so important. Supremum over all dyadic intervals of the average of W times average of the W inverse. Notice that it's metric in the sense that the A2 constant of W is the same as A2 constant of W inverse. Right, and I will need the dyadic BMO definition. The BMO space is the bounded mean oscillation space. So the bounded mean oscillation over dyadic intervals should be the mean oscillation of over the dyadic intervals should be bounded. It turns out that in the dyadic case we can write it as the supremum of such average sum. Okay, and this is something that we will need. So maybe I will write the A2 definition and the BMO, this BMO norm here. Okay, so let's see. The A2 norm, W, A2 to be MIW, MIW inverse, and the norm of the BMO norm of anything will be here, this, sup over I, here's sup over I in the dyadics, 1 over the length of I, sum of the VHI squared. Okay? And let's see. And now, who is the perfect dyadic operator? The perfect dyadic operator is an operator associated to the kernel K that satisfies standard size condition. And instead of standard cancellation conditions, we are imposing perfect cancellation conditions. Instead of asking for this being small, we ask for this being 0 on the dyadic intervals. X and X prime, where X and X prime belong to interval I, Y and Y prime belong to interval J, as long as I and J are disjoint. Both this and this, K does not change. Okay? So let's see. Let's analyze how K should look like. This thing. Let's think of how should K look like. So, let's see. Oh, green, sorry. Probably black. Okay, so whenever I pick an interval I can split it into two halves, into I plus and I minus, in the X and in the Y, right? And I will be looking at the I cross I. And whenever my Y's are in I plus here, and X's are in I minus which is a point here, my function should be a constant here. My k should be a constant, right? And my k should be a constant here as well. And then I keep going, yeah? Having a constant here, right? And having my kernel to be constant here all over the place, right? You can see the pattern. So how does the k look like? Here it will be 0 and 0, right? Here I will call this constant to be ki, well, say minus, since x belongs to the a minus. And here I'll say that it's ki plus. Okay? And so on and so forth. So let's see. Here it is. So k has to be constant on the I plus cross I minus because they do not intersect. The plus stands for the right child, the minus stands for the left child of the interval I. Right? And then ki plus is defined to be the value of the function of the kernel k on the whenever x belongs to I plus y to I minus, and k or I minus whenever x belongs to the I minus and y then hence belongs to the I plus. And it has to be 0 because of the decay condition, because of the size condition, or whenever your x and y have different numerical sign. All right? Then our kernel can be written this way, as it's ki plus whenever you are in the product of I plus times I minus, right? It's ki minus whenever you are in the product of I minus times I plus. And then operator can be written this way. Right, you just integrate, this is what you get. Again, this fi minus is the integral of f over I minus, fi plus is the integral of f over I plus. Okay, now when we understand how the operator looks like, here is the main theorem, that if a weight w belongs to, is an A2 weight, then a perfect dyadic operator T, whenever perfect dyadic operator T satisfies the T of 1 conditions, that T of 1 and T star of 1 belong to the BMO, and I have them bounded by constant Q because this constant appears here, right? And the weak boundedness property, or the testing condition, I'm testing my operator on just Haar functions and dotting them with Haar functions. If this thing is uniformly bounded, then my operator is bounded in L2, nothing new there. In L2 of W, nothing new there. But moreover, it's bounded linearly with respect to the A2 constant of the weight W. All right. Now, a little bit of history. Helson and Segeau proved that the Hilbert transform is bounded on the weighted spaces, right? Then Hunt, Mackenhaupt, and Witten came up with this A2 condition, right? They have had a different proof, and this A2 in particular condition arose, right? Then Koifman and Pfefferman extended their results, their proof to a larger class of operators. Boni defined the paraproduct operator, continuous paraproduct. I probably didn't need to put it here. Since we will put, it doesn't matter. But then the important part is the T of 1 theorem of David and Journet of 84, which basically says the following. It says that, it says that whenever you have a Calderon-Zygmunt operator T, then you can write it as a very nice operator, which is almost a convolution, plus a paraproduct with the T of 1, and plus the adjoint of the paraproduct with T star of 1. All right, and this is how their proof goes. You can bound para product and its side joint, and then L is good enough in order to obtain bound for the operator, right? All right. Of course, they do not trace the constants. And, well, L2W dependence anyway. Okay, in 2002, Osher, Hoffman, Moscalu, Tao, and Tilly showed very nice results on the dyadic, for the perfect dyadic operators. They obtained new versions of the T of 1 and T of B theorems, so-called local. We are not very interested in the results, but they did it for the perfect dyadic operators. And later in 2008, O'Shea and Yang, and I believe it's a PhD thesis of Yang, were able to extend their results to the whole family of Calderon-Zygmunt operators. So possibly, think of this work as being a work in progress. The aim is a bound on the, not just perfect dyadic, but Calderon-Zygmunt singular integrals. And maybe it's possible this way. Some partial results for the Calderon-Zygmunt operators are known. The linear bound is known to hold for Hilbert trees, Berling transform. Many people did it. It's known for families of convolutional singular integrals with very hard conditions on the kernel. Published result, however, I believe is power 3/2 for the C-infinity kernels. And it's, I think, due to Lerner. Okay, so this is a history. Now let's go into the proof. So we have an operator, let me remind you, an operator T that has this form, right? Okay. The first thing that we would like naturally to do, since we are following the T of 1 theorem, is to evaluate T at 1, right? And T star at 1. Put it into the para product and subtract it from there, right? But when you evaluate T at 1 and T star at 1, put it into the para product, you get something really huge, and I wasn't able to get any bound out of that. So what we are going to do, we will try very gently to separate this operator into parts and then bound each part. Okay? So here is the integral, here is the operator. So how does it look like? Again, it's T of F equal to the sum Ki plus F over I minus characteristic function of the I plus Ki minus Fi over I plus, the integral of F over I plus, characteristic function of the I minus. What this is, if you look at this, it's on the interval I, it's some coefficient times the characteristic function of the left side, right? Plus some other coefficient times the characteristic function of the right side, right? Which can be represented as some average, I don't know, I'll say A times the characteristic of I, right? Plus some other coefficient B times the Haar function of I, right? Yeah? Then what are A and B? A and B are the average of Ka plus F over integral of F over I and K average of K and Ki minus integral of F over I plus, right? Which we can also represent in a very similar way as in certain coefficient times F dot characteristic function plus F dot the Haar function, right? So let's see. Oops. Show, hide. Okay, and this is what we are doing. So when you write it very carefully out, you're getting that T is sum of 4 operators. There are some differences, but it doesn't matter. T1, T2, T3, and T4. Yeah? And it turns out that all 4 operators are our good friends. Let's see. This operator T1 was very deeply researched by Nazarev, Trail, and Wahlberg. This T2 and T3. T3 is the dyadic paraproduct operator, and T2 is its adjoint. And here are the paraproducts, except they are not quite paraproducts with T of 1 and T star of 1 anymore. And this one is the martingale transform, which was also researched by Janine Witwer. Okay. So, but in order for those operators to be bounded, we need certain conditions. We need to derive certain conditions on the k's, on those coefficients, ki plus minus, ki minus, and ki plus plus ki minus. All right? So let's see what is given to us. Let's see what is given. We have the T of 1 conditions, right? We know that the T of 1 has to have BMO norm bounded by a constant, right? And T star of 1. What happens, let me go back for a second, when you put function 1 into the T? When I average function 1 over an interval I, I'm getting 1. Oh, I'm getting length of I, right? When I'm dotting function 1 with the HI's, I am getting 0. So these 2 parts will disappear. These 2 will stay, right? So let's see. Yeah. These 2 parts stayed. The other 2 disappeared. We do the same for the T star of 1. Well, you can write rewrite T star in a similar way, put function 1 in, and get this thing. All right. The next thing we do is we need to bound its BMO norm, which means I put T of 1 here, I dot it with an H, I square it, and then I add it over all the subintervals of I, right? So let's first dot it with an H. Let's look at the T of 1. When I dot it with the H sub j, the second part, when I dot hi with the hj, the only thing that I'm getting is when I is equal to j, right? So we will have this when I is equal to j, h's are normalized in L2, right? Their dot product is 1. Okay, now what happens here is you will have all the i's that are in the left half of the j, and all i's in the right half of the j will produce you the coefficients, right? When I'm taking the average, when I'm dotting the characteristic function of I with the hj, right? And similar way we proceed with the with the T1 star. Notice that the only difference between T of 1 and T star of 1 is it's positive there and it's negative over here. So in one case, this second sum will be, which will be just one term after we dot, will be with positive, and the other case was the negative. Okay, so here they are dotted with the hj, right? Absolutely the same difference of 2 sums, and then the plus or minus some coefficient bj, right? Yeah? What we can deduce from here is that sums of the square of the, let's see, is that the sum of the over all the j inside some interval I of this bj squared is bounded, averaged over the length of I, okay? So we square the bj, we get difference of ki plus minus ki minus squared times the length of j to the 3. All right, and here it is. I mean, Q just keeps, this coefficient in front of Q. Q is something that bounds that's involved in the standard size condition on the kernel. T bounds the BMO norm of T of 1 and bounds from above the, no, that's all. Yeah, that's all. Yeah, I think that's all. Yeah, the cancellation condition is trivial, is perfect as 0, right? All right. In about the same way, we get, simpler that from the testing conditions, we obtain this. This bound for the ki plus ki minus times length of I squared. And let me put this thing on the blackboard. Let's see, on the white thing. So what do we know about the coefficients kj? We know that for every dyadic interval j, 1 over the length of j, sum of over I in the dyadics of j, of the ki plus minus ki minus squared times the length of I cubed is bounded from above by 16q, and we know that it's actually squared, I think. And we know that 1 over the length of j, sum over the I belonging to the dyadics of j, ki plus ki minus, plus minus are on the top, times the length of I squared is bounded by also some constant 8q. Okay, I have the absolute value here, and I forgot to mention. Now, this is just the size condition on the kernel, right? And this is the condition which I think is unnatural and can be removed, but it's a technical condition I need for one of the theorems I'm going to use. So I will assume that at least some of the ki plus and ki minus for every dyadic interval is non-negative. Okay. So in principle, you do not need an absolute value anywhere. Okay, so let's see. So once again, we have our operator. Our goal is to bound each part, T1, T2, T3, and T4, by a bound linear with respect to the A2 constant, right? So let's see. Let's first bound the two old good friends, the T2 and T3. Okay? T3 is the dyadic paraproduct operator, which is bounded linearly with respect to the A2 constant of the weight W. Whenever the function B that you're having this product with belongs to the BMO, which means this for the coefficients Ki. For the KIs. I want square of of my coefficients here to be summable over I, when we sum it over I belonging to the dyadics, or all the dyadic subintervals of some interval j, and then average divided by the length of j to be bounded by the constant q. Then I get a linear bound in q and in A2. Okay? Now, the operator T2 is the adjoint of my dyadic paraproduct. Now, since my A2 conditions are absolutely symmetric, then T2 will be bounded on the A2 of W, right? The adjoint. Whenever W inverse belongs to the A2, and the bound will be linear with respect to the W inverse norm, right? W inverse constant of the weight W. But since the constant of the W inverse is equal to the constant of W, everything goes through, right? By symmetry of the A2. Good? So 2 are gone. T4. T4 is a result of Janine Witwer in 2000. She shows that it is bounded by the linear bound in the L2 of W. Whenever we have that those coefficients are bounded uniformly. But this is nothing but our size conditions on the kernel, right? With a constant C here equal to 2. By the way, constant C all over the place is different. And even if I use it in the same inequality, it doesn't have to be the same. Okay? All right. Okay, good. And by the way, this result is sharp. So the linear bound here is optimal, which maybe it holds from there that the linear bound on the perfect dyadic operators is optimal as well. I don't know good proof of it yet. I didn't think about it. Okay, so, and now finally the most complicated creature is the T of 1, T1 thing. But thanks to Nazarov, Trail, and Wahlberg, they took care of it. They have this theorem that often is we refer to this theorem as the bilinear embedding theorem, which says that for the non-negative sequence of numbers alpha I, whenever you can prove these three top inequalities, then you can prove the bottom one. Bottom one is just the bound on T1 by duality and nothing else. Okay? So if we use this theorem with this V equal to the W inverse and W equal to W, and what should be my alpha i's? So let's see. I'm using it with V equal to the W inverse. And then alpha i's have to be my coefficient ki plus plus ki minus times the length of I. And now let's see, I have mi here, the average here, and average here. There I have an average times the characteristic function. I need to add another length of I squared there, right? All right. And then what it will say that if I use it with that alpha I and the V equal to the W inverse, I will obtain the bound and the norm of the operator T1. Right? Yeah. Yeah, that's what it says. Right? Yeah, V equal to the W inverse, alpha I equal to that. And then when you put this alpha and V into the inequalities, these are three inequalities that you need to prove. In order to have the linear bound on the operator T1. Good. So let's see. First bound is trivial. Why? Because look, what stands here, this thing is the A2 constant of the weight W. Yeah? And this thing, ki plus plus ki minus times the length of I squared, sum of those here is bounded by my conditions, by the weak boundedness properties, or by my testing conditions, assumptions on the operator T from the very beginning, right? Now, these two bounds are completely symmetric. We can just show one of them. The other one is absolutely similar, except you have to replace W by W inverse. And the second inequality is done by the following little lemma, that if your V is a weight, I need a little bit more here. I need V and V inverse to be locally integrable. And let lambda I be a Carlson sequence such that this holds. Then we have, well, skip a couple of lines, we have this bound. Yeah? On the MIV or MIW, lambda I is equal to the ki plus plus ki minus. This is again the testing conditions work. Okay, and then proof of the theorem is complete. So we have a linear bound on the perfect dyadic Calderon-Zygmunt operator. So, and it's very reasonable. Here is our operator. T splits into parts, T1, T4, T2, T3, right? T2 and T3 are paraproduct and it's adjoint, right? T1 and T4, in the original theorem, they were almost self-adjoint. Here they are self-adjoint, yeah? And admit very nice bounds. And the other thing is, that's what Steve Hoffman pointed, that the bound on the paraproducts come indeed from the fact of the boundedness of T of 1, of the T of 1 belonging to the BMO and T star of 1 belonging to the BMO. And bounds on the T4 and T1 come from the second bound from the testing conditions. Okay, I think I'm done. Thank you very much, and thank you, I would like to thank organizers for inviting me. Thank you. Well, in the paper by Hoffman, Tao and Tilly and Osher and Moskalu, they're doing it for the dyadic trees. Perhaps. So, yeah, yeah, probably the right reference is the reference on that paper. And they obtain actually very, very nice versions of the T of 1, T of B theorems. They call them local theorems. They're very useful. I think they're a little bit easier to use. I would like maybe to go through their proofs, but yeah. Well, I mean, to make this look a little bit more like their proofs, but you know. Yeah. Any other questions?